It is my great pleasure today to have Dr. Zhan to visit us today. Dr. Zhan was my collaborator a few years ago. We worked on one work together. And right now he is a professor in the School of Electronic Science and Engineering at the Nanjing University in China. He is actually familiar to this area. He received his PhD degree from New York University in 2011. Dr. Ma's research focuses on computational imaging in the brain called media communications. And today he's going to talk about his group's latest work on neural video coding.
Okay, thanks for having me here, and thanks people to come into this talk. I will give some discussion for what we have done for past years. It's called neural video coding. Basically, we try to solve the problem about this video traffic. Besides these 60 texts used to develop in here in lab, and source coding still matters because of the traffic grows exponentially. But unfortunately, what do we really care in video? There are two major society. One is called compression society. We care about the bits. We want to have the bits perfectly reconstructed. So it leads to several well-known codecs used in cell phones, like X.64, VVC, AV1. Today when you watch the YouTube, most of them are using AV1. That's the one society. Another is even bigger society. That's called the vision society. You may know that like ImageNet, Fei Li, and these guys. For those guys, they care about the semantics. What do we really see the objects in the video? For those like well-known vision engines such as YOLO, SAM, and HRNet, they are popular names in this society. But unfortunately, for these two societies, they somehow parallelize, and over decades, they rarely talk to each other. But in fact, our neural vision, so our visual pathway, is doing it together. When we see the thing, we're actually doing the understanding. So the retina captures the physical world, and through the light, and this light convert to the electrical signals and go through the visual pathway layer by layer to extract important information for the understanding and for the task inference. So this task can be the classification, can be the segmentation, and can be the recognition. So for the past decades, some of the neuroscientists using the high-end imaging system showing that our visual pathway is remarkable coder. It can achieve the compression ratio about like a 2 to the 5 compression factor. In comparison, the latest standards developed by like more than thousands of the experts and invested by millions of dollars, it only achieves like a 10 to the 3 factors. We still have like 100 factors to go. And in the meantime, our brain can do this remarkable recognition, classification, and that's the brain's advantage. So in the past years, our lab is doing this brain-inspired coding. We try to unify the multitasks into one coder. So previously, most of the people have the connection with the coding and the compression. But frankly speaking, the coding is a tool and the compression is a task. So now we try to have this multitasking. So coding for the compression and coding for the semantic understanding. So like recently the automotive industry, they're doing this autopilot. They use this camera to understand the world. And let's go visit this hierarchical visual coding program. Actually, this is what the neuroscientists done for the past decades. So the lights arrives the retina using the photoreceptor like the rods and cones to convert them to the electrical signals and go through this RGC, retinal ganglion cell, and LGN, and goes to V1, and even beyond the V1 for the high-end areas. From the photoreceptor for the V1, I think is we are started for the past years, but beyond that, it's not we are started. Still have a lot of work to do. So from this one, we can see that the visual signal is processed step by step. It's very different from what they do for the past years. For example, for the video codecs, they incoming frame and we split frame into blocks. And for each block, we try different modes or different tools to use minimum bits to represent it. But this is totally different from what we have done in the visual pathway. So when I back to the Nanjing University in 2014, I tried to learn from the hierarchical visual coding in our brain and try to develop this new paradigm for the visual coding. And luckily, we have a lot of learning tools available since the AlexNet. And after that, we developed this called hierarchical VAE. You know, the VAE is one powerful tool, variational autoencoder, to do the signal modeling, to do the data modeling. But before that, most of VAE only using one layer called the hyperparameter VAE. One similar paper was published by it's called Jonas Ballet. Now in Google, they use this hyperparameter VAE to do the image coding. But in that way, the performance is limited. So we extended the hyperparameter VAE to the hierarchical VAE. We can do a lot of layers. When you see this kind of paragraph, you can see that you can have the idea that when we have the frame, for example, a 4K image, we do the downsampling. Our brain is doing downsampling. And here we use the VAE to do the convolutional downsampling. And backwards, when you have the lowest layer, we code it. So from the ZT1, that's the lowest spatial resolution, we code using some like bits, and we recurrently refine it to the highest layer of the reconstruction. So it's called a hierarchical VAE. And the only key problem we want to solve is when we code the symbol, we need to know exactly probability of that. So the problem is translated to we need to do the accurate prediction of the conditional probability. So this is very strictly strictly proved in our paper published last year, and it's called quantized aware ResNet VAE. And you can see that the probability when we go from the low layer to the high layer, the prediction accuracy is getting accurate and accurate. So we can do the data modeling even better compared with, for example, right now, the hyperparameter VAE or other like diffusion models. And then when we go to the implementation, nowadays the students are very familiar with the PyTorch and the AI platforms. You can just using the PyTorch these tools like the convolution, like the ResNet block to stack them together. The bottom up is doing the downsampling. You can think about this is for any given images, you get this multi-scale observation. And this multi-scale observation is through the REST block. And once you get to the lowest spatial resolution, you go up to encode layer by layer, scale by scale. So the latter block in the dash blocks, that's the key blocks we use to code them into the bit stream. And here, here, apparently you can see that this is a scalable solution. And the scalable solution actually for the video streaming is very attractive to the industry people. Since right now, for most of the codecs used in the video streaming, we have to prepare different versions of the bit rate. For example, Dash or HLS. When you click the iPhone this version, they prepare actually a lot of versions with different resolution and different bit rate. But here, inspired by this brain processing, we inherently provide this scalable solution. So from the low resolution to the high resolution, using this latter block to encode them. And in this, we only have the residual connection from the current frame. And when you code the frame here, we use the probability or use the prior from the previous frame. So you can see here, M here. M is the reference from the previous frame. So we only use the reference from previous frame to form the context feature for the probability estimation. In this way, we somehow avoid the motion estimation used in traditional codec for decades. Now everything is the probability generation and the probability estimation. So in other way, this is the reason why our code is so fast and why our code we can achieve the real time. And here comes the distribution. In the efficient coding theory developed for the neuroscience, they have some like assumption saying that, okay, if you have the data for any given image close to the zero mean Gaussian, it will be more likely the brain encoded the scene. So for the A here is the paper published by Google. This image coding using the hyperparameter and the autoregressive for the probability estimation. But you can see here, it's not zero mean. It's quite offset from the zero. And you can see the standard deviation is quite large. So the encoding of the image is not as good as the video. This DVC is the video and the DCVC is the video. And they use the residual coding. When you're doing the residual coding, you can see here is kind of the zero mean Gaussian. But apparently the DCVC using the conditional coding, it's not simply doing the subtraction to get a residual. And you can see here the standard deviation is much squeezed compared with the DVC. So that's why the Microsoft solution is much better than this DVC. And then later, our solution is like, that we're doing scale by scale. So only for the first layer, we only have this learnable constants. We have this kind of zero mean, not as good as the videos, but for the higher scales, scale 2 for scale 4, we have the prediction from the low layer. Our distribution is more like the zero mean Gaussian and more squeezed, even compared with the DCVC. So that's why our performance is better with compressible lattice. And here the VCT is the one published by the Google last year. This one is more similar to ours to avoid using explicit motion estimation. So if you are using explicit motion estimation between frames to get the motion or tracking or trajectory, it's very complicated and it won't help us to get a real-time processing. And here is the performance. So PSR-wise, we are still a little bit lower than the DCVC produced by the Microsoft. And MSE-wise, actually, ours is quite comparable. Compared with others, commercialized codecs like the HVC, VVC, our solution is much better. And the reason is that we have this solution is we now is the lowest complexity. You can see here, our solution, DHVC, can ramp up to the 30 frames per second for the decoding and the 20 frames per second for the encoding. But we are encoding RGB now. RGB is 3 channels. But if we convert it to the YUV and the subsample YUV, we can have the 1080p at real time. So this is the first time we have this learned codec into the real-time processing. And we are using very old GPU in China, since now the high-end GPU cannot be purchased in China. And the advantage of the real-time processing and the performance, I believe is just attributed to the hierarchical processing architecture. And from now on, we only this kind of development can enlarge the application scenario. We are not only present papers using compression society like the RD's redistortion. We are now can allow this codec to run on the real time. We can do streaming. We can do even for the internet, these kind of applications. With parallel, we somehow can manage to do the scale by scale pipeline.
Each scale gets its own pipeline.
Yeah, each scale gets its own pipeline. So now for each frame, we have 4 scales. Previously, we need to finish the 1 frame, go to the next frame. Now, for the pipeline solution is if we finish the scale 1 of the first frame, we can go to the scale 2 of the next frame. So that's a parallel. Yeah, it's pipelining. And we can share the parameters. So for scale by scale, we can also share the parameters. So that's why our models gets to the less parameter compared with other solutions. And especially we get a much lower memory, running memory. Since now you have to buy a very expensive GPU for the higher end memory. For example, now the DCVC, it uses like 13 giga when you run it. That's impossible for the consumer level GPUs. I'm using the 3090. Yeah. And now it's 2090 and 5090. And for most of the this kind of learning, most people using the A100, H100. but those GPUs are prohibited in China. Yeah. Okay, this is about the compression. That's one task. And no, somehow people think that, okay, we have some other equivalent, but when we test them, it's much poor performance compared with NVIDIA. So NVIDIA is still the most powerful player in this area. Yeah, keeping the same NVIDIA.
So computational wise, is there a possibility like a future neural network processing units in the phone will actually be benefited by this one?
Oh yes, we are now. My student is currently all the results are tested using NVIDIA using the PyTorch, and then now we are migrating this setup to the M4.
Yeah.
So the Apple chips. So yeah.
Well, I think it might be benefited by having the whole memory and all the things.
Yes, that can be even better. So we expect that one to the M4 will be much faster, and then we can do using two M4 iPad. We can do this video conferencing. So we can simulate a lot of things there.
Streaming and
yeah.
That's something your group is working on.
Yeah, that's something we are working on. Since the hierarchical structure give advantage, we come here to see that okay, we can do the progressive decoding. So before, when you receive a packet, for example, from Netflix, you decode it, render it to the TV. That's one resolution. But now, since we have different scales for different resolutions, you can choose to render at any scale. For example, if you have sufficient bandwidth, you can choose to render the 4K. And if you not have sufficient bandwidth, you can choose to render at the 20p. So that's the scales meaning. So column-wise is a frame order from the first frame for the feature frame. And the lower-wise is latent scale. So for example, if you only have received 3 scales, you still can see clearly about the contents. But if you have more scales up, you can get a better results and better quality. That's the progressive decoding. And upon this progressive decoding, we also invest the packet job. Since the network is unexpected, so somehow when you're doing these Wi-Fi's, you have packet job. Previously, if you have packet job, you have to do the ARQ, resend the packet, or you can use FEC. But if you use FEC, you somehow offset the compression you have done. Yes. So both of the results are complained by the networking guy. You are not to solve the conjecture of the network. So here, since we have different scales, for example, here we have the packet loss at the 5th frame. So everything before 5th frame decoded perfectly. But after first frame, you can see the frame 6 and frame 7 are impacted since the highest scale of the packet is lost. But when you lost this scale, the receiver knows which scale is lost. So immediately the receiver sends the echo to the encoder. And once the echo is received by the encoder, okay, for the 8th frame, so he can choose. We are not using any reference from temporal one, since the temporal one is corrupt, and we can limit our reference from the current frame only. So we call it resynced. So the error propagation will be terminated. That's also another attractive design by this hierarchical structure. For the around 2000 times when we developed the ABC, in that time people are expect this kind of functionality, but in that time when we're doing this traditional codec, it's really hard to support this functionality. But now when we have this AI, we can do this. And this is the hierarchical. We can improve the performance. We can have the parallel processing, and we also can have this network-friendly design.
Just a quick question. So when the packet jobs actually happen, so frame 6 and frame 7 will have a drop in the quality?
Yes.
Okay.
Yes.
And then it suddenly come back at 8 because it actually dropped local buffer.
So the 8th frame, we are not choose the 7, the highest scale for the prediction. Since you know that.
Oh yeah, because you need to reproduce on the lower.
We need to do the probability estimation using the reference from either current frame low scale or from the previous frame, the same scale.
Okay.
Yeah, since the frame 5 has these jobs at the high scale, so the ACE will choose not to do the temporal prediction anymore. We only rely on the current frame. That somehow cut off the error propagation across frames.
Okay.
Yeah.
So maybe frame 9 or frame 10 then will have go back to resolution.
Yes, yes, yes.
I see.
So this is just the simple example for our recent publication, and we are trying to emulate all the network patterns for the Wi-Fi, for the 4G, 5G, and even for the satellite. So they have different packet job patterns, and use that packet job patterns will drive the implementation of this codec. Then we come to the semantic multitasking. So previously we all about the coding for the communication to reduce the bandwidth consumption, to help the network-friendly design. And here we come to the semantic multitasking. That means that we try to think about the things currently for all these vision tasks, for these vision engines, they acquire this information from the RGB, right? We use a camera in the car, we use a camera installed on the front door and capture the RGB. And from the RGB, we analyze the feature, we analyze the length, we analyze other activities. But somehow in our brain, we never do that. In the middle of our brain processing, we don't come to the retina to have these pixels and to get this information to analyze and do the decision. We're actually using the processing intermediate representation, we call it latent representation, directly go to the high level of the brain cortex to do the decision. So that's the assumption we have. And we go back to the latents we produced by the learned codec and the other codecs. We can see that it somehow has some hypothesis that the learned codec can produce the basis of the visual things. And this basis will be linearly summarized to produce the reconstruction using a set of coefficients. And if you don't want the reconstruction, you want to do the semantic understanding, for example, classification, we can use another set of the coefficients. So we only have difference of the coefficients, but the latent is the same in the brain. So by this assumption, we do this very simple student-professor learning. So the pixel domain models is what we have right now using in application like YOLO, like SAM. And it takes X, RGB, to produce anything, classify the faces or classify the lengths. And here, the compressed model, we reproduce the pixel domain models. Instead of input the X, the original image, we input the latent. The latent is actually encoded. So it's kind of like the intermediate representation after the encoding to mimic what we have in the brain visual pathway. So with this pixel domain as the teacher and the compressed domain as the student, we somehow can do this transformation, and this transformation is linearly. We just need to do the weights linear transformation, and we can do we can directly feed the Z instead of the X to do the application oriented to these tasks. And we verify this with classification and segmentation. You can see here, the second column is decode and using ResNet. That's the things have been done in the industry right now, using anything like the YOLO right now. And what we have right now is ResNet AA, we call this adaptation. So we won't go back to the pixel reconstruction. We directly use the Z to do the classification. You can see here the top one accuracy is quite similar. And the latency, if you want to do the decoding, you have a lot of latency. For example, the 257 microseconds. But if you don't go to the pixel reconstruction, you only have the 10% of them. It's really fast. It's also very good to use in those latency critical scenario. For example, the autopilot. So you cannot wait another 200 microsecond to decode to the image space and to the detection. So that's the thing right now. I know that the Tesla has done something like this. So we won't go to the pixel domain, just using the compressed representation, go into the classifier or segmentation directly. Segmentation, we also done this one. And then now we also verify the recognition. So anything you can think about very popular vision tasks, we can do in the compressed domain. Yeah. And this thing also open another problem is like previously we have this video retrieval over the internet, mostly rely on the tags, right? People tag the video and we can search on the YouTube, on the Hulu or Netflix. But if you have this functionality enabled, we can actually use bitstream to search bitstream. We don't need to rely on go back to the pixel domain. Since previously we have to go back to pixel domain and do a lot of stuffs for the engine to search these videos. But now we can do the bitstream level manipulation. So it will be go very fast to do this retrieval or the search. Okay, later, since now we are 2D one, later we also extend this hierarchical structure to the 3D, mostly about the point cloud. We recently have this month has these two papers published about the point cloud compression. So we are the first one to support the point cloud, for example, the LiDAR, and also like the 4D performance using the in AR VR glasses. If you have the Vision Pro, you can see very vibrant and fantastic display of the 3D in the glasses. And now we have this another one is from the Meta, right? The very cheap one. Ray-Ban produce these smart glasses. So this one is open. Another question is whether we can do it in the 3D. And unfortunately, our hierarchical structure just need to change the 2D conversion to 3D conversion. We can do everything similarly like the videos and the images. And surprisingly, we have this frameworks. We have very good results. This is a similar structure: downscaling, 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 and encoding the lowest scale using the lowest scale as a prior to predict the probability of the next layer. So all is about the probability estimation. I think that's the basic course from the EE students. And our performance now is the cutting edge. To me, I think the most probably is the soda. We compare with the standardized solution, we only need like 10% of the bitstream and produce the same quality of the reconstruction. And recently, the standard committee has issued this call for the next generation learning-based point cloud compression. Our is the candidate for that one. Yes, I'm the unicorn. You can see here. We only need like 80% of the B-rates compared with the GPCC. So that's the minus is the BD measures. So that's the information theory measures. It is different application driven. For the AR, VR, this 4D performance, probably we use the VPCC. But if you use LiDAR for this automotive industry, we use the GPCC. Yeah, very sparse one. Then we also extended this hierarchical processing from the RGB to RAW. That things motivated me many years ago when I was working for the Samsung. In that time, Samsung has different types of displays. They have the OLED, they have LCD, they have LED. And only if you render this video content, the image content to the display, you will perceive the colors. Before that, all the images or videos, you want to go to see them from the compressed format. So that has the one question is why in our camera we have this ISP, we call the image signal processor, right? And for the surveillance video footage, we have these surveys on the internet saying that over 99% of the surveillance video never being seen by anybody. So that's the question is why our camera using like 50 years, this paradigm, CMOS plus ISP plus the disks or plus the network to save it. So come with the question. And also another one is like, I talked to some like startups for the autopilot. They say that, okay, if you want to license the camera from big names, Nikon or Sony, they have pay like 30% of the cost to the ISP. So that's the reason we see that, okay, whether we can remove this ISP, since the ISP is somehow is the intermediate steps to process the raw signal in the CMOS. CMOS is to use to simulate our eyes, to collect the lights and to integrate them and have these images. So have these assumptions, we propose this, we call it raw vision. Why not we do everything from the raw, from the CMOS, right? And we can using this AI to do the compression. If you want to streaming these things, and since we have the raw, once you receive this compressor raw, you can use ISP to reconstruct for the rendering for display. As long as you want to see the RGB, right? Then we can save a lot of bandwidth, save a lot of energy here. And if you want to do the object detection, we can also do in the raw directly. We also prove that, okay, now, not like the 30 years ago, we have very poor CMOS technology. So in that time, we use ISP to improve the quality of the acquired things. But now the CMOS technology is way advanced compared with ISP. For example, for the autopilot, we usually use like 18 bits of the CMOS. But for most of the image we see, for example, ImageNet or on the internet, we have 8 bits. So it somehow is degraded the reconstruction quality. So that's also another reason we go back to the raw. When you capture, for example, in the phone, when you capture, anytime you capture it, you will use ISP.
What's the processing delay of?
Processing delay, for example, if you have this 30 frames per second real time, the processing delay at least is 30 milliseconds. You have to go through this 30 milliseconds to get it done before the deadline of next frame.
You're saying that if we get rid of ISP just to save the raw format,
Yes,
we can be
you can avoid this.
seconds for each
For
image.
yes, for our test, it's kind of like a 5 milliseconds. You can save more than 70% of the latency. Yes, this project we have done 4 years. And when we submit paper to the PAMI, and one reviewer asking us, if you want to claim this latency reduction, power reduction, you build a real system and using the real system show our results. So for 2 years, we built this system here. We're using an AI camera module produced by some company. I think it's still in the US. The right bottom line is what they have done right now, used in the industry, using the RGB one. When you capture the raw image, we convert them to the RGB, and then on this RGB, they do a lot of like models for detection. And if we go back to the raw, yes, and when we have this processing on the raw only, we have this raw vision framework. You can see that stepwise, we cut a lot of steps from raw to the RGB, right? And we tested them using a lot of images. And you can see here, that's the average gains. We normalize them to the RGB vision, used to be used in this SoC. And the classification accuracy without any change of the models, we have like 3%. If you look up the CVPR papers, you can see that they do a lot of careful design of networks. They only can have like 1.5 and 2% that they claim, okay, this is significant improvement. But now we just move the RGB to the raw. We have 3% gains. And you can see the latency and the power cost. The latency, when we remove this raw to RGB, we have saved 70% of the latency, and then we saved more than half of the power. So you don't need any raw to RGB processing, so that the power can be down a lot. And then the camera even more like green, right? Energy efficient.
There is a question related to that. I mean, there are a lot of things that are done in the processing of sensor input that before you get to RGB, meaning say white balance. I mean, there are a lot of things that cameras do
Yes,
to adjust for the condition.
yes.
So how would you see that? I mean, that would have to sort of be built into the model somehow.
We completed remove them. We believe that the accumulation of the photons is the actually natural reflection of the physical scene, and we use that to feed the, for example, YOLO, feed the yes.
So I mean, how do you? Okay, so I'm not sure I really know how human eyes are processing, but we do adjust, right?
Yes,
A lot of things.
when you go to the human perception, you definitely need a white balance, definitely need the illumination change, brightness change.
Yeah, exactly.
But for the machines, they do another way. So that's the major inspiration for me is like machine may not use the same paradigm as human does.
Human vision versus a machine vision.
Yeah, as long as you have the information there, without any connotation, without any information degradation, you can use that information to sort of, yeah.
So that's actually, and the reason why I'm thinking about how this is going to work, really, how they have these, the famous dress where somebody sees it in one color, somebody sees it in the other color.
Yes.
Then you have all those jokes, then they put
Yeah.
pattern with dots and stuff and say, do you see X or do you see R or something?
Yeah.
That is the consequence of white balance and all the adjustments. So how will machine react to that, right?
Yes.
It's not clear. And we are talking about semantic, right? So I'm really thinking about semantic. If somebody asks machine, is that dress color A or color B? What will machine say, right? Is it going to be the same perception or same semantic as what I?
Yes, if you want to have this, we call it color correction, you still need a lot of data to train the machine to know that. And this is also problem was like reported 3 or 2 years ago when Tesla have this,
Absolutely.
yeah,
White sky, white truck, white.
yeah, this accident.
So basically, you need another model to convert machine, like those raw footage saved by machine back to some human understandable image.
When you want
If you
to,
want to review the stream.
if you want to review it,
recording.
yeah.
Okay.
If you don't want to review it, you just get rid of all of them.
Yeah, because you don't
Like a surveillance video, only one.
Yes, right.
Yeah. Yes.
Yeah, but I'm just putting it in the context, like, is it a person in a white dress or a person in a black dress? Or,
Yeah.
I mean, how is that going to work, right? I'm not saying that's the most important.
Yes.
But it becomes an issue, right?
Yes, when you want to view it, you can using the ISP learned to create that human perceivable these RGBs. Yeah, and also this is advantage nowadays. You know that the people why buy this high end camera because Nikon, Canon, or Leica they have very patented this ISP.
Yeah.
But when we have this learning stuff, we can reproduce this kind of similar colors like the Leica, like Canons using our cell phone. We have done this before, so we're doing these mappings. And here is the results. You can see here RGB baseline is used right now in the industry. Train use RGB and test use RGB. And we do this naive baseline, like, okay, we have loss, so we send it into RGB. And you can see that recall and AP is significantly degraded, more than 10%, right? And when we're doing our unpaired cycle R2R, we first generated this simulated raw to train the model, and we use the real raw captured to test it. And you can see here we have the even higher recall and a higher AP compared with the RGB baseline. I think that's because we have this raw without any degradation of the bit precision. And here, yeah.
Basically, you review the whole data set to get everything in raw.
Yes.
Okay, that's a huge data set and a lot of work to do.
That's why we call this unpaired cycle R2R. We don't need to supervise. We don't need to one by one pair. Since you cannot have like 2 cameras, one is capture the raw and one is capture RGB to supervise them.
Huge. So you know iPhone 16?
You know,
Pro, they can only take around 10 minutes 4K raw video shoot before they fill up the memory. Like
I
a
mean,
two
okay,
pieces.
I know what BMP is. So raw is just like, there's more bits per pixel compared to BMP.
The only thing is like is that currently raw has higher bit precision. If you go to BMP, you may cut it to the 8-bit.
Yeah.
Yeah, but the raw, the advantage of raw is it has a lower spatial resolution. Since for one pixel area, you have the RGB or ROIB. So it's 4 pixel going to the 1 pixel. And when you get up to the 4K, actually it's having the demosaic. So for that one, it's like a quarter of the resolution compared with what we see for the RGB. But we have 4 channels, RGB or ROIB, like this way. Yeah, but the other thing is like it has like 8 bits per channel. But now we have like RGB, we have 18 bits per channel. But RGB, we have 8 bits. That's the things of the raw, why it's so big.
Now I have another question about the raw formats between different sensors.
They are different. They are different.
And the model need to train specifically by the sensor. Does it need to be trained? Like
We just need to get some very few, like the 2 or 3 snapshots of that camera.
different, if there are different sensors, so basically you just need to fine tune the country, fine tune your model to adapt that sensor.
Yes, yes.
Wow.
That's the things here. I think you have a very good question and the insights. Here is we're using the average, the raw we simulated.
Oh.
And this if we have pre-trained, we just need a little bit, like the 2 or 3 data to retrain. And you can see they were to fit to the individual cameras. If you have, in the application scenario, you may have one specific camera.
Yeah.
This camera you just need like a 10 images or 5 images.
But that's RGB image.
Raw image.
Raw zero.
Yeah,
image. Okay.
yeah, raw image. So here we have no RGB image anymore.
You're right. Because I think retrain, you need to.
Since this raw image is to let the unpaired psychoadva to learn what is the specific sensor characteristics.
So basically, you need to have a reference image across all the cameras. So every time you take the first ever image of that CMOS, you should still always have the same image. So you have a calibration standard.
No need to have the similar images. Yeah, anything. That's unpaired and unsupervised.
Oh, that's why.
Yeah.
Okay.
Yes. So we only need to learn the distribution of the sensor.
Oh, okay.
Yeah.
You don't even care about content or color.
We don't care about content. Yeah. And here is the compression results. This is the classification results. This is the compression results. Since most of the raw, you see the iPhone, right? iPhone use some of the standards that Cinema DNG or JPEG XL to compress the raw losslessly. And we just fine tune what we have for the learned codec. For example, 1% we're just using one raw image captured by this specific camera. And you can see here our performance is even better compared with the JPEG XL. So that's the lossless. And for the lossy one, our results are even better compared with the VVC, the latest one. You can see here, this is the VVC latest one, and this is ours. So the performance is significantly improved. And this is the interesting things I tell before. It's like when we have the raw, you can see a lot of objects, right? We max them, and if you go back to the 8-bit, some of them are missed, and that's because of the bit precision problem. Yeah, and this area is actually acquired by our lab. We drive the car around the Nanjing city, and you can see we have different scenario. In the early morning and in the late night, we have this night lens flare. I think that's very important for the autopilot. Okay, I think.
So this can maybe also adapt to different kind of CMOS. For example, thermal cameras, IR cameras, they can actually see way more than, as long as you can convert their sensor CMOS output to raw.
Yes. And the raw here is just the accumulation within a period of time of the fountains.
Oh, okay. Yeah. So it's more adaptive to any cameras.
Yes.
And then, or maybe they can install thermal cameras on auto-driving cars.
Yeah, even for LiDAR.
LiDAR?
Yeah, even for LiDAR. That's also the accumulation of the reflect the laser pulse.
But if the library is point cloud.
No, you can accumulate it to. Yeah, you can accumulate.
Raw.
Yeah.
Wow. Never seen crazy.
Before point cloud,
Flashlight.
yeah. And now they have another called event camera. Event camera. So event camera captures the brightness change. When you have motion, you have bright change.
Oh, okay.
Yeah, that's even faster. Now we have the camera, for example, consumer level go up to the 240, right? But the event camera, you can go up to like thousands, even like 10,000 frames per second. So that one is now widely used in this kind of high-speed detection. Yeah, one of the Nature just published recently is using the event camera plus the normal camera to capture the unexpected the motions when you're doing this autopilot. Yeah, it's from the ETH. I think ETH is the very first groups they doing this event camera. Yeah. Okay, this is a summary of what we have done for the past decade. So 2012 is AlexNet. And our lab probably the first one to propose this learned video codec in 2017. And we participated a lot of like international context. For example, we have the 2020 best performing and the 23 best algorithm paper. And now 2024, we have this real-time neural video coder. I think that is anticipated by the industry for a long time. And the industry, before they are very hesitant to do this neural video coding because they think that it's too complex.
It's based on CNN, right?
Yes. Yeah, everything is convolution. The training I think is less than 1 day. Yeah, it's very. Our model actually is like you can think about currently video coding is image coding, and yeah, every is image coding since you can pipeline, and you use the encoded stuff previous frames to do the probability. So we don't have the motion estimation anymore. So you don't need to wait for the finish of the previous frame to do the next frame. That's the reason why we are so fast. And interestingly, our performance is also good. Yeah.
With the single code, it doesn't need to be.
Yeah. Yeah, we can have a single coder to support like previously coded frame coding, video coding, and we can support all the bit rates. So that we can do the networking stuff. Yeah.
The rate, as you said, is still not as good as some of the more time consuming.
Yeah. Yes. Yeah. And we also help another the company to do this called we call the emergency image communication. For example, nowadays you can see a lot of people wear these Garmin watches. And the Garmin watch has GPS. When you go to some mountain area, you don't have this what we call the territory communication for 4G, 5G. You have emergency, you want to call this help, we can use the GPS channel. The GPS channel is around this 375 bytes per minute. So we compress this image to this narrow band and let the people know where you are. And what we have helped the company do that. Here we just give some like sample images. We now have even better results right now. You can see here compared with GPX 2K and ours, you can clearly identify which area you have. Sorry about this Chinese word, this location of somewhere. Yeah. So when you have this, we can help these people who love the mountain rider, right? You can go to GPS now. And okay, this is the open source. We are gradually put all the things open source, not only models. So we want the community to use it and to promote it. So that's the thing we have done. Yeah, this is my lab.
Yeah, I mean,
You have a large group, 20 students per group.